Imagine standing beneath a starlit sky, gazing up at the countless points of light scattered across the darkness. Each twinkle, each gentle glow, represents light that has traveled unimaginable distances to reach your eyes. Some of these photons began their journey thousands, even millions of years ago, racing through the void at what we consider the ultimate speed limit of our universe. For over a century, scientists have told us that nothing can move faster than light. This invisible boundary, set at precisely 299,792,458 meters per second in a perfect vacuum, has become the cornerstone of our understanding of physics. It governs how we measure time, how we calculate distances across the cosmos, and how we comprehend the very nature of reality itself. But tonight, as you listen to these words and perhaps drift towards sleep, consider this question that has captivated physicists and dreamers alike. What if everything we thought we knew about speed was just the beginning? What if light, despite being the fastest thing we have ever measured, is not the final word on velocity in our universe? The speed of light seems impossibly fast to us here on Earth. In just 1 second, a beam of light could circle our planet more than 7 times. It could travel from Earth to the Moon in less than 2 seconds. Yet in the grand scale of the universe, even light seems to crawl. The nearest star beyond our sun is so far away that light takes over 4 years to make the journey. The light from distant galaxies that we see through our most powerful telescopes left those celestial bodies billions of years ago. This creates a profound mystery. If light is truly the fastest thing possible, then the universe becomes a lonely place, where civilizations, separated by vast distances, could never hope to communicate in real time, where space travel to even nearby stars would take generations, where the cosmos itself imposes limits on what we can explore and understand. But what if there are ways around these limitations? What if the universe has hidden pathways, secret mechanisms, or undiscovered phenomena that could allow information, energy, or even matter to travel faster than light? What if the speed of light is not a wall but merely a hurdle waiting to be overcome? Throughout history, humans have repeatedly discovered that what seemed impossible was simply waiting for the right understanding, the right technology, or the right perspective. We once believed that heavier objects fell faster than lighter ones, until Galileo showed us otherwise. We thought time was absolute and unchanging, until Einstein revealed its flexible nature. We assumed space was empty and static, until we learned it could bend, stretch, and even tear. Perhaps our current understanding of the speed of light will join this list of revised scientific truths. Perhaps future generations will look back at our era and smile at how we thought light speed was the ultimate boundary, much like we might smile at ancient maps that marked unknown territories with the words here, "Be dragons." Tonight, we embark on a journey through some of the most fascinating and mind-bending concepts in modern physics. We will explore theoretical particles that might move faster than light, investigate quantum phenomena that seem to ignore distance entirely, and consider exotic structures in space-time that could serve as cosmic shortcuts. We will examine the work of brilliant scientists who dare to question what seems unquestionable, who push the boundaries of our understanding, and who remind us that the universe is far stranger and more wonderful than we often imagine. We will discover that even if nothing can move faster than light in the conventional sense, there may be ways to sidestep this limitation entirely. As you settle in for this exploration, remember that science at its best is about wonder, curiosity, and the courage to ask difficult questions. The question of whether anything can be faster than light touches on the deepest mysteries of existence. How does information travel? What is the true nature of space and time? Are there aspects of reality that we have not yet discovered? These questions do not have easy answers, and that is precisely what makes them so compelling. In seeking to understand the limits of speed in our universe, we are really seeking to understand the limits of possibility itself. We are asking whether the cosmos has built-in boundaries that constrain what can happen, or whether these apparent boundaries are simply invitations to think more creatively, more boldly, and more imaginatively about the nature of reality. So let your mind wander as we begin this journey. Allow yourself to consider possibilities that might seem impossible, to entertain ideas that challenge everything you thought you knew about how the universe works. Because in the realm of cutting-edge physics, today's impossibility often becomes tomorrow's breakthrough, and the most profound discoveries often come from those brave enough to ask whether what everyone knows to be true might actually be just the beginning of a much larger and more extraordinary story. To truly understand whether anything can be faster than light, we must first grasp what makes light so special, so fundamental to the very fabric of our universe. Light is not just the illumination that allows us to see the world around us. It is one of the most profound and mysterious phenomena in all of physics, a cosmic messenger that carries information across the vast emptiness of space. When we speak of the speed of light, we are referring to a very specific number, 299,792,458 meters per second in a perfect vacuum. This might seem like an arbitrary figure, but it represents something far more significant than just how fast photons travel. This speed is woven into the very structure of space and time itself. Imagine light as the universe's ultimate courier service. Every second, beams of light carry messages from distant stars, bringing us images of cosmic events that happened long ago. The light from our sun takes approximately 8 minutes and 20 seconds to reach Earth, which means that when you look up at the sun, you are seeing it as it appeared more than 8 minutes in the past. This delay becomes even more remarkable when we consider more distant objects. The light from the nearest star system, Alpha Centauri, takes over 4 years to reach us. The magnificent spiral galaxy Andromeda, visible to the naked eye on clear nights, appears to us as it existed 2.5 million years ago. When we look through powerful telescopes at the most distant galaxies, we are seeing them as they were billions of years ago when the universe itself was young. But light is more than just a messenger from the past. It defines the very concept of simultaneity. According to the principles of physics that govern our universe, there is no such thing as universal now. Events that appear simultaneous to one observer might occur at different times for another observer moving at high speed. This strange reality emerges directly from the properties of light and its invariant speed. Consider this remarkable fact. No matter how fast you are moving, light always appears to travel at the same speed relative to you. If you are standing still and measure the speed of a passing beam of light, you will get the same result as someone traveling at tremendous velocity who measures that same beam. This constancy of light speed is one of the most counterintuitive yet fundamental aspects of our universe. This property of light connects directly to how we measure distance in space. When astronomers speak of objects being light years away, they are using light itself as a cosmic ruler. 1 light year represents the distance that light travels in 1 Earth year, approximately 9.5 trillion kilometers. This unit of measurement highlights how intertwined light, space, and time truly are. The speed of light also determines how quickly information can travel from one place to another. In our daily lives, we have become accustomed to nearly instantaneous communication. We send messages across the globe in fractions of a second, video chat with people on other continents, and access information from servers thousands of kilometers away. Yet all of this apparent instantaneity is made possible by electromagnetic signals, which are simply forms of light, traveling at light speed. Even our most advanced communication satellites and fiber optic cables are bound by this fundamental limit. The signals they carry cannot exceed the speed of light, which means there will always be some delay, however small, in long-distance communication. For most Earth-bound applications, this delay is negligible, but it becomes significant when we consider communication across astronomical distances. This limitation has profound implications for space exploration and the search for extraterrestrial intelligence. If we detected a signal from a civilization orbiting a star 100 light-years away, it would take a full century for our reply to reach them, and another century for their response to return to us. A simple conversation would span multiple human generations. The speed of light also plays a crucial role in defining energy and matter. You may have heard of Einstein's famous equation E equals mc squared, where c represents the speed of light. This equation reveals that the speed of light is not just about motion, but about the fundamental relationship between energy and mass. The enormous value of c squared means that even tiny amounts of matter contain tremendous quantities of energy. This relationship explains why accelerating objects to light speed becomes increasingly difficult as they approach that velocity. As something moves faster and faster, it requires more and more energy to continue accelerating. At speeds approaching light speed, the energy requirements become infinite, which is why most physicists believe that nothing with mass can ever quite reach light speed, let alone exceed it. Yet light itself, composed of massless particles called photons, travels at this ultimate speed effortlessly. Photons are born traveling at light speed and can never slow down or speed up. From the moment a photon is created until it is absorbed by something else, it maintains this constant velocity through space. Understanding light also means understanding electromagnetic radiation in all its forms. Radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays are all the same fundamental phenomenon, differing only in their wavelength and energy. All travel at identical speed through vacuum, regardless of their energy or frequency. This universality of electromagnetic radiation speed suggests something profound about the nature of space itself. Empty space is not truly empty, but filled with invisible fields that allow electromagnetic waves to propagate. The speed of light may actually be telling us something fundamental about the properties of space and time, rather than just about light itself. As we drift deeper into this exploration, consider how remarkable it is that this one number, the speed of light, connects so many seemingly different aspects of reality. It links energy to matter, defines the flow of information, determines how we measure cosmic distances, and establishes the rate at which cause and effect can propagate through the universe. But perhaps most intriguingly, the speed of light may not represent an absolute barrier so much as a fundamental characteristic of the space and time we inhabit. If space and time themselves can be bent, stretched, or folded, then perhaps the limitations imposed by light speed are not as absolute as they first appear. Perhaps the universe has ways of allowing information, energy, or even matter to effectively travel faster than light, without actually violating the fundamental principles that make light speed so special. The history of measuring light speed is itself a fascinating journey through human ingenuity and scientific discovery. For centuries, people debated whether light traveled instantaneously or had a finite speed. Ancient Greek philosophers like Aristotle believed light transmission was instantaneous, while others suspected it might have a measurable velocity. The first serious attempt to measure light speed came from Galileo Galilei in the early 1600s. He and an assistant stood on hilltops several kilometers apart, each holding a lantern. Galileo would uncover his lantern, and his assistant would uncover his own lantern as soon as he saw Galileo's light. By measuring the time delay, Galileo hoped to calculate light speed. Unfortunately, light travels so fast that human reaction time made this method impossible. The first successful measurement came from an unexpected source: astronomy. In 1676, Danish astronomer Ole Rømer was studying the moons of Jupiter when he noticed something peculiar. The timing of eclipses of Jupiter's moons seemed to vary depending on Earth's position in its orbit. When Earth was farther from Jupiter, the eclipses appeared to happen later than predicted. When Earth was closer, they occurred earlier. Rømer realized that this timing difference was due to light taking time to travel the varying distances between Earth and Jupiter. By carefully measuring these timing variations, he calculated that light speed was approximately 214,000 kilometers per second. While not perfectly accurate by modern standards, this was remarkably close to the true value and represented humanity's first successful measurement of this fundamental constant. Over the following centuries, scientists developed increasingly sophisticated methods to measure light speed with greater precision. In the 1800s, French physicist Hippolyte Fizeau used a rotating toothed wheel to measure light speed over terrestrial distances. Light would pass through gaps between the teeth, reflect off a distant mirror, and return. By spinning the wheel at just the right speed, the returning light would be blocked by the next tooth, allowing Fizeau to calculate light speed with unprecedented accuracy. American physicist Albert Michelson refined these techniques even further, using rotating mirrors and precise timing mechanisms. His measurements in the late 1800s were accurate to within a few kilometers per second of the true value. Michelson's work was so precise that it contributed to the discovery that light speed appears constant, regardless of Earth's motion through space, a finding that would later prove crucial to Einstein's theories. Today, we define the meter itself in terms of light speed. Rather than using a physical object as the standard for length, we define 1 meter as the distance light travels in 1,299,792,458th of a second. This means that light speed is now exactly 299,792,458 meters per second by definition. This seemingly arbitrary decision reflects the profound importance of light speed in physics. It suggests that light speed is more fundamental than our human concepts of distance or time. In a sense, light speed provides the universe's natural units for measuring space and time, and our human measurements are just convenient approximations of these deeper cosmic standards. The constancy of light speed has implications that extend far beyond simple measurement. It means that light itself serves as a universal reference frame, a cosmic constant that remains the same regardless of the motion of the observer or the source of the light. This property makes light speed unique among all known velocities in the universe. Consider what this means for our understanding of motion itself. In everyday experience, velocities are relative. If you are walking forward in a moving train, your speed relative to the ground is the sum of your walking speed and the train's speed. But light does not behave this way. Light emitted from the headlight of a speeding spacecraft travels at exactly the same speed as light emitted from a stationary source. This bizarre property of light challenges our intuitive understanding of how motion works. This constancy also means that light speed represents a kind of cosmic speed limit that applies to the transmission of information and energy. No signal, no influence, no cause and effect relationship can propagate faster than light speed. This creates what physicists call a light cone, a region of space-time that defines what events can influence each other. The light cone concept helps us understand why faster than light travel would be so revolutionary. If something could travel faster than light, it could potentially carry information outside the light cone, creating the possibility of effects preceding their causes. This would fundamentally challenge our understanding of causality itself. Yet the universe seems to be constructed in such a way that light speed serves as more than just a speed limit for material objects. It appears to be a fundamental property of space-time itself, determining how space and time are related to each other. This deep connection between light speed and the structure of reality suggests that understanding light speed is really about understanding the nature of existence itself. Even in the quantum realm, where particles can exist in multiple states simultaneously and can appear to influence each other instantaneously across vast distances, the speed of light remains a crucial boundary. While quantum entanglement allows particles to be correlated in ways that seem to transcend distance, no information can be transmitted faster than light through these quantum connections. This has led some physicists to wonder whether light speed represents a fundamental limit built into the architecture of our universe, or whether it might simply be a characteristic of the particular region of space-time we inhabit. Could there be other domains of reality where different rules apply, where the speed limit is different, or where the very concept of speed has different meanings? The speed of light also plays a crucial role in determining the large-scale structure of the observable universe. Because light takes time to travel, and because the universe has a finite age of approximately 13.8 billion years, there is a maximum distance from which light has had time to reach us. This creates what astronomers call the observable universe, a sphere centered on Earth with a radius of about 46 billion light-years. Beyond this boundary lies the unobservable universe, regions of space from which light has not yet had time to reach us. These regions might contain galaxies, stars, and perhaps even life, but they remain forever hidden from our direct observation. The speed of light thus determines not just what we can see, but what we can ever hope to see. Understanding light speed also helps us comprehend why the universe appears to be expanding. When we observe distant galaxies, we see them as they were billions of years ago. The light from these galaxies has been stretched by the expansion of space during its journey to us, causing the galaxies to appear redder than they actually are. This redshift provides crucial evidence for the expansion of the universe and helps us understand its history and fate. As we settle deeper into this exploration of cosmic speed limits, it becomes clear that light speed is not simply a number that describes how fast photons travel. It is a fundamental constant that defines the relationship between space and time, determines how information can flow through the universe, and establishes the ultimate rate at which cause and effect can propagate. But perhaps most intriguingly, the speed of light may not represent an absolute barrier so much as a fundamental characteristic of the space and time we inhabit. If space and time themselves can be bent, stretched, or folded, then perhaps the limitations imposed by light speed are not as absolute as they first appear. Perhaps the universe has ways of allowing information, energy, or even matter to effectively travel faster than light, without actually violating the fundamental principles that make light speed so special. Light, the ultimate constant in our universe, shapes everything we know about reality. But could there be something that challenges this fundamental limit, something that opens up possibilities we have not yet imagined? In 1905, a young patent clerk named Albert Einstein published a paper that would forever change our understanding of space, time, and the speed of light. Working in relative obscurity in Bern, Switzerland, Einstein proposed ideas so revolutionary that they challenged everything humanity thought it knew about the fundamental nature of reality. His special theory of relativity didn't just describe the speed of light. It revealed that light speed is the cosmic thread from which the entire fabric of space and time is woven. Einstein's breakthrough came from wrestling with a profound puzzle that had troubled physicists for decades. The equations describing electromagnetic phenomena, developed by James Clerk Maxwell in the 1860s, predicted that light should travel at a specific speed. But this raised a troubling question: speed relative to what? In everyday experience, we measure speed relative to something else. A car travels at 60 kilometers per hour relative to the road, but if that car is on a moving ferry, its speed relative to the shoreline is different. Scientists initially assumed that light must travel relative to some invisible medium filling all of space, which they called the luminiferous ether. Just as sound waves travel through air and water waves travel through water, they reasoned that light waves must travel through this ethereal substance. If this were true, then Earth's motion through the ether should affect the measured speed of light in different directions. In 1887, Albert Michelson and Edward Morley conducted one of the most famous experiments in the history of physics, attempting to detect Earth's motion through this supposed ether. They used an ingenious device called an interferometer, which split a beam of light in two, sent the beams in perpendicular directions, then recombined them to look for tiny differences in their travel times. The result was completely unexpected and deeply troubling to physicists of the time. No matter how they oriented their apparatus, no matter what time of year they conducted the experiment, they found absolutely no difference in light speed in any direction. The ether, if it existed at all, seemed to have no effect on light speed whatsoever. Einstein approached this puzzle from a radically different angle. Instead of trying to explain away the constancy of light speed, he embraced it as a fundamental postulate. He proposed that the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This simple statement, combined with the principle that the laws of physics should be the same for all observers moving at constant velocity, led to conclusions that seemed to defy common sense. If light speed is truly constant for all observers, then something else must change to accommodate this constancy. That something, Einstein realized, was space and time themselves. When objects move at high speeds relative to each other, space contracts and time dilates in precisely the amounts needed to keep light speed constant for all observers. Consider what this means for a spacecraft traveling at 90% of light speed. To an observer on Earth, the spacecraft would appear compressed in the direction of its motion, shortened by more than half its original length. Meanwhile, clocks aboard the spacecraft would appear to run slowly, with 1 second on the spacecraft corresponding to more than 2 seconds on Earth. But here's where Einstein's insight becomes truly mind-bending. From the perspective of someone aboard the spacecraft, they would see themselves as perfectly normal, with their ship at its usual length and their clocks running at normal speed. Instead, they would observe Earth as contracted and Earth clocks as running slowly. Each observer sees the other's space contracted and time dilated, yet both perspectives are equally valid. This reciprocal nature of relativistic effects reveals something profound about the nature of reality. There is no absolute reference frame, no universal perspective from which space and time can be measured objectively. Space and time are not fixed stages upon which events unfold, but rather dynamic aspects of reality that change depending on the observer's motion. Einstein's equations showed that as an object with mass approaches light speed, its length contracts towards zero, its time dilation approaches infinity, and the energy required to accelerate it further increases without bound. At exactly light speed, the equations predict that a massive object would have zero length, infinite time dilation, and would require infinite energy to maintain its motion. This mathematical impossibility suggested that nothing with mass can ever quite reach light speed. Yet light itself, composed of massless photons, exists in a strange realm where these usual rules don't apply. Photons are always born traveling at light speed and can never slow down or speed up. From a photon's perspective, if such a perspective has meaning, no time passes during its journey from source to destination, regardless of the distance traveled. A photon that traveled from a distant galaxy for billions of years experiences its entire journey as instantaneous. This special status of light speed led Einstein to realize that it represents something far more fundamental than just the speed of electromagnetic radiation. Light speed is the speed at which space and time are connected to each other. It's the rate at which cause and effect can propagate through the universe, the maximum speed at which information can travel from one place to another. Einstein's general theory of relativity, published in 1915, extended these insights to include gravity and acceleration. General relativity revealed that massive objects actually bend the fabric of space and time, creating what we experience as gravitational attraction. Even more remarkably, it showed that space and time are not just related to each other, but are aspects of a single four-dimensional entity called space-time. In this unified view of space-time, the speed of light represents the conversion factor between space and time dimensions, much like the exchange rate between different currencies. Just as you need an exchange rate to convert dollars to euros, you need the speed of light to convert between measurements of space and measurements of time. General relativity also revealed that gravity affects the passage of time. Clocks run more slowly in stronger gravitational fields, an effect that has been precisely measured and must be accounted for in GPS satellites orbiting Earth. Time literally passes more slowly, closer to massive objects, and this effect becomes more pronounced as gravitational fields become stronger. Near the event horizon of a black hole, where gravity becomes so intense that not even light can escape, time dilation becomes extreme. To an outside observer, time would appear to slow down dramatically for anything approaching the event horizon. At the event horizon itself, time would appear to stop completely from the outside perspective, though someone falling into the black hole would experience time normally from their own perspective. These extreme gravitational environments also affect light itself. While light always travels at the same speed locally, its path can be bent by curved space-time. Light from distant stars is deflected when it passes near the sun, an effect that was first observed during a solar eclipse in 1919 and provided one of the first confirmations of Einstein's general relativity. Even more dramatically, intense gravitational fields can stretch light waves, changing their color and energy. Light climbing out of a deep gravitational well becomes redshifted, losing energy as it fights against gravity. Light falling into a gravitational well becomes blue-shifted, gaining energy as gravity accelerates it. These effects reveal that space-time itself is a dynamic, flexible medium that can be stretched, compressed, and curved by the presence of matter and energy. The rigid, absolute space and time of Newton's universe gave way to Einstein's malleable space-time, where geometry itself becomes a physical phenomenon, subject to the influence of mass and energy. This flexibility of space-time opens up intriguing possibilities. If space-time can be curved by matter and energy, might it be possible to curve it so severely that distant regions of space are brought closer together? Could space-time be folded, twisted, or even torn in ways that might allow for faster-than-light travel without violating the fundamental principles of relativity? Einstein's equations don't necessarily forbid such exotic possibilities, though they would require forms of matter and energy, with properties unlike anything we've ever observed. Some solutions to Einstein's field equations describe theoretical structures like wormholes, which could potentially connect distant regions of space-time through shortcuts that bypass the usual limitations of light-speed travel. The relationship between matter, energy, space, and time described by relativity also leads to another famous equation, E equals mc squared. This formula reveals that mass and energy are interconvertible, with the speed of light squared serving as the conversion factor. The enormous value of c squared means that tiny amounts of matter contain tremendous quantities of energy, explaining the power of nuclear reactions and the energy output of stars. But perhaps most importantly for our exploration of faster-than-light phenomena, Einstein's relativity provides the theoretical framework within which any such phenomena must be understood. Relativity doesn't necessarily prohibit faster-than-light travel, but it does establish the rules that any such travel must follow to avoid logical paradoxes and violations of causality. As we drift deeper into these cosmic mysteries, we begin to see that Einstein's great insight was not just about the speed of light, but about the interconnected nature of space, time, matter, and energy. His theories revealed that the universe is far stranger and more flexible than our everyday experience suggests, opening up possibilities that earlier generations of scientists could never have imagined. The speed of light, rather than being a simple speed limit, emerges as a fundamental aspect of the geometry of space-time itself. Understanding this geometry and its flexibility may hold the key to discovering whether the apparent barrier of light speed can be transcended without violating the deeper principles that govern our universe. Relativity tells us that light speed is a boundary that cannot be crossed by conventional means. But are there unconventional means, exotic phenomena, or undiscovered aspects of space-time that might provide exceptions to this seemingly universal rule? Imagine you could step aboard a spacecraft capable of traveling at 99% of the speed of light. As you accelerate away from Earth on a journey to a distant star, something extraordinary would happen that challenges our deepest intuitions about the nature of time itself. While you experience time normally aboard your ship, time on Earth would appear to flow much more rapidly. Years would pass on Earth for every month that passes for you. This strange stretching and compression of time, known as time dilation, reveals one of the most profound and counterintuitive consequences of approaching light speed. Time dilation is not science fiction or theoretical speculation. It is a measured, verified aspect of reality that affects everything from subatomic particles to massive spacecraft. Every day, scientists observe particles created in cosmic ray collisions lasting much longer than they should because they are traveling at speeds close to light speed. GPS satellites orbiting Earth must account for time dilation effects, or their navigation systems would accumulate errors of several kilometers per day. To understand how time dilation works, we must first abandon our intuitive notion that time flows uniformly throughout the universe. In our everyday experience, time seems absolute and universal. A second on Earth lasts the same duration as a second anywhere else, and events that are simultaneous for one person are simultaneous for everyone. Einstein's relativity reveals that this apparent universality of time is merely an illusion created by the relatively slow speeds at which we normally move. The mathematical relationship governing time dilation is both elegant and startling. As an object's velocity approaches the speed of light, time dilation becomes increasingly dramatic. At 50% of light speed, time passes about 13% more slowly. At 90% of light speed, time slows down by more than half. At 99% of light speed, time dilation becomes so extreme that 1 year aboard a fast-moving spacecraft corresponds to more than 7 years on Earth. But perhaps the most famous illustration of time dilation is the twin paradox, a thought experiment that has captivated physicists and philosophers for over a century. Imagine identical twins, Anna and Beth. Anna remains on Earth while Beth embarks on a journey to a star 20 light-years away, traveling at 99% of the speed of light. From Earth's perspective, Beth's round trip takes approximately 40 years, but due to time dilation, Beth experiences only about 6 years during her journey. When Beth returns to Earth, she finds that Anna has aged 40 years, while she has aged only 6. The twins, once identical in age, now differ by 34 years. Beth has literally traveled into Earth's future, experiencing firsthand the relativity of time that Einstein predicted. This scenario might seem to create a logical paradox. After all, from Beth's perspective during the journey, shouldn't Earth appear to be moving away at high speed, causing time on Earth to run slowly? The resolution of this apparent paradox lies in the fact that Beth's journey is not symmetric. While Anna remains in a single reference frame throughout the entire experiment, Beth must accelerate away from Earth, decelerate at the distant star, accelerate back toward Earth, and decelerate again upon arrival. These periods of acceleration break the symmetry and result in Beth aging less than Anna. The twin paradox illustrates a profound truth about the nature of time and motion. Time is not a universal constant, but a personal experience that depends on one's motion through space. Each observer carries their own clock, their own measure of time's passage, and these personal times can differ dramatically depending on the observer's velocity. Time dilation affects not just mechanical clocks but all physical processes. Chemical reactions, radioactive decay, biological aging, even the oscillations of atoms all slow down equally when moving at high speeds. This universality of time dilation suggests that time itself, rather than just our measurement of it, is what changes with velocity. Consider what this means for space travel to distant stars. Even with conventional rocket technology that could achieve only a small fraction of light speed, interstellar journeys would take thousands or millions of years. But with spacecraft capable of reaching speeds very close to light speed, time dilation could make such journeys feasible within a human lifetime from the traveler's perspective. A journey to the Andromeda Galaxy, 2.5 million light-years away, would take at least 2.5 million years from Earth's perspective, even at light speed. But for travelers aboard a spacecraft moving at 99.999% of light speed, the journey might feel like only a few decades due to extreme time dilation. The travelers could literally cross intergalactic distances within their own lifetimes, though millions of years would pass on Earth during their absence. This possibility creates poignant scenarios for future space exploration. Astronauts embarking on relativistic interstellar journeys would be essentially traveling one way through time, as well as space. They might return to find that Earth's civilization has advanced by thousands or millions of years, that the languages they spoke are no longer understood, that the people they knew are long dead, and that humanity itself might have evolved beyond recognition. Time dilation also affects how we understand the relationship between space and time in the universe. As objects approach light speed, not only does time slow down, but lengths contract in the direction of motion. These two effects are intimately connected, representing different aspects of the same underlying phenomenon, the geometry of space-time. From the perspective of someone traveling at high speed, the universe itself appears contracted in the direction of travel. Distances to destination stars appear shorter, making the journey time reasonable even without considering time dilation. Meanwhile, observers at the origin and destination see the traveler's spacecraft as contracted and their clocks as running slowly. These reciprocal effects reveal the deep symmetry underlying Einstein's relativity. There is no absolute perspective from which space and time can be measured objectively. Each observer experiences their own space and time as normal, while observing other reference frames as distorted. This relativity of space and time measurements reflects the fundamental structure of the universe itself. Time dilation becomes even more extreme in the presence of strong gravitational fields. Near black holes, where gravity is so intense that space-time itself is severely curved, time dilation can become virtually infinite. An observer falling toward a black hole would experience time normally from their own perspective, but to someone watching from a safe distance, the falling observer would appear to slow down dramatically as they approach the event horizon. At the event horizon of a black hole, gravitational time dilation becomes so extreme that time appears to stop completely from the outside perspective. Light from the falling observer becomes increasingly redshifted and dimmed until it fades beyond detection. From the outside universe's point of view, nothing ever quite crosses the event horizon, remaining frozen at that boundary for eternity. Yet from the perspective of someone falling into the black hole, time continues to pass normally. They would cross the event horizon and continue falling toward the singularity at the center, experiencing their final moments in normal time, even as the outside universe appears to speed up around them. These extreme time dilation effects near black holes have profound implications for our understanding of space and time. They suggest that time is not just relative, but can be stretched to such extremes that it essentially stops from certain perspectives. This malleability of time opens up intriguing possibilities for time travel and the manipulation of temporal flow. Some theoretical physicists have proposed that sufficiently advanced civilizations might use controlled gravitational fields to create time dilation effects for practical purposes. By surrounding a habitat with an intense gravitational field, inhabitants could experience time more slowly relative to the outside universe, effectively extending their lifespans from an external perspective. Conversely, by carefully positioning themselves in regions of space-time where gravitational time dilation causes time to pass more quickly, travelers might be able to journey into the future more rapidly than normal time passage would allow. While such scenarios remain highly speculative, they illustrate how time dilation opens up possibilities that seem magical, yet are grounded in well-understood physics. Time dilation also affects our understanding of simultaneity across vast distances. Events that appear simultaneous to one observer may occur at different times for another observer moving at high speed. This relativity of simultaneity means that there is no universal now, no moment that can be identified as the present throughout the entire universe. This breakdown of absolute simultaneity has profound implications for faster-than-light travel. If something could travel faster than light, it might be possible to arrange scenarios where effects occur before their causes, creating logical paradoxes that challenge our understanding of causality itself. This connection between faster-than-light travel and causality violation represents one of the strongest theoretical arguments against the possibility of exceeding light speed. Yet time dilation also suggests that the boundaries imposed by light speed may be more flexible than they initially appear. If time itself can be stretched and compressed, if the flow of temporal experience can be manipulated through motion and gravity, then perhaps there are ways to transcend the apparent limitations of light speed without violating the fundamental principles of causality. As we explore these temporal mysteries, we begin to see that time dilation is not just a curious consequence of high-speed travel, but a window into the deeper nature of space-time itself. The malleability of time reveals that our universe is far stranger and more flexible than our everyday experience suggests. At near light speeds, time itself begins to bend and stretch, showing us that the universe operates according to principles that transcend our ordinary understanding. But could this bending of time suggest that light speed is not the ultimate limit, but merely a boundary waiting to be transcended through deeper understanding of space-time's hidden properties? As we have explored the seemingly absolute nature of light speed and its role in shaping space and time, a natural question emerges. If nothing can exceed this cosmic speed limit through conventional means, might there be unconventional pathways that sidestep this restriction entirely? The universe, in its infinite creativity, may have provided mechanisms that allow information, influence, or even matter to effectively travel faster than light, without technically violating the principles of relativity. These alternatives to conventional faster-than-light travel fall into several fascinating categories, each representing a different approach to transcending the apparent limitations imposed by light speed. Some involve hypothetical particles that naturally exceed light speed. Others propose manipulating the fabric of space-time itself to create shortcuts between distant regions. Still others explore quantum mechanical phenomena that seem to ignore distance altogether. Perhaps the most intriguing of these alternatives involves theoretical particles called tachyons, whose very existence would require them to travel faster than light at all times. Unlike ordinary matter, which requires infinite energy to reach light speed, tachyons would require infinite energy to slow down to light speed. They would inhabit a mirror universe of velocity, where faster than light travel is not just possible, but mandatory. If tachyons exist, they would possess properties that seem almost magical from our ordinary perspective. They would travel backward through time from the viewpoint of some observers, arriving at their destination before leaving their origin. They would become more energetic as they slow down and less energetic as they speed up, exactly opposite to the behavior of ordinary matter. Most remarkably, they could potentially carry information instantaneously across any distance, making real-time communication possible between the most distant regions of the universe. Yet despite decades of searching, no tachyon has ever been detected. The absence of tachyons in our observations might simply reflect the limitations of our current technology, or it might indicate that the universe has some fundamental principle that prevents such particles from existing. Some physicists argue that tachyons would create logical paradoxes that make their existence impossible, while others suggest they might exist but be impossible to observe directly. Another fascinating alternative to faster-than-light travel involves the manipulation of space-time geometry itself. Einstein's general relativity reveals that space and time are not fixed, absolute entities, but dynamic aspects of reality that can be curved, stretched, and folded by the presence of matter and energy. If space-time can be manipulated sufficiently, it might be possible to create shortcuts that allow effective faster-than-light travel without actually exceeding light speed locally. The most famous of these geometric shortcuts are theoretical structures called wormholes, which would connect distant regions of space through tunnels in the fabric of space-time itself. A traveler entering one end of a wormhole might emerge from the other end in a completely different part of the universe, having traveled vast distances in minimal time without ever exceeding light speed during the journey. Imagine space-time as a vast sheet of paper representing the three-dimensional universe. A journey from one side of the paper to the other would normally require traveling across the entire surface. But if the paper could be folded so that distant points touch each other, a tiny hole punched through both layers would create a shortcut that dramatically reduces the travel distance. Wormholes would function as similar shortcuts through the higher dimensional fabric of space-time. The mathematics of general relativity do permit wormhole solutions, but they come with significant challenges. Most theoretical wormholes would be extremely unstable, collapsing so quickly that nothing could pass through them. Keeping a wormhole open long enough for travel would likely require exotic forms of matter with negative energy density, something that has never been observed and may not exist in nature. Even more speculative are proposals for manipulating space-time expansion itself. The universe is expanding, carrying distant galaxies away from us at speeds that can exceed light speed. This expansion doesn't violate relativity because the galaxies themselves are not moving through space faster than light. Rather, space itself is expanding between them. Some theoretical physicists have proposed that sufficiently advanced technology might create localized regions of space, time expansion and contraction, effectively surfing on waves of expanding and contracting space. The most famous of these proposals is the Alcubierre warp drive, conceived by physicist Miguel Alcubierre in 1994. The Alcubierre drive would contract space in front of a spacecraft, while expanding space behind it, creating a wave of distorted space-time that carries the ship along. From the perspective of someone aboard the spacecraft, they would remain stationary within their local bubble of normal space-time, while the universe moves around them. Such a drive could theoretically achieve any speed, even exceeding light speed from the perspective of distant observers, without violating relativity, because the spacecraft itself never moves faster than light through its local space-time. The ship would ride within a bubble of normal space, while the bubble itself moves through the cosmos at arbitrary speeds. However, the Alcubierre drive faces enormous practical challenges. The energy requirements might exceed the total mass energy of observable objects in the universe. The drive would require exotic matter with negative energy density to function. Even more problematically, recent analyses suggest that the drive might be fundamentally impossible due to quantum effects that would destabilize the warp bubble. Yet another approach to transcending light speed limitations involves quantum mechanical phenomena that seem to operate outside the normal rules of space and time. Quantum entanglement, perhaps the most mysterious aspect of quantum mechanics, allows particles to become correlated in such a way that measuring one particle instantly affects the other, regardless of the distance separating them. Einstein famously called this quantum entanglement spooky action at a distance because it seemed to violate the principle that nothing can influence distant events faster than light speed. When two particles become entangled, they form a single quantum system that transcends ordinary notions of locality. Measuring the spin of one entangled particle instantly determines the spin of its partner, even if the partner is on the other side of the galaxy. This instantaneous correlation occurs without any signal traveling between the particles, which might seem to suggest that information can be transmitted faster than light through quantum entanglement. However, the strange nature of quantum mechanics prevents this phenomenon from being used for faster-than-light communication. While the correlations are instantaneous, extracting meaningful information from them requires comparing measurements made at both locations, and this comparison must be done through conventional, slower-than-light communication channels. Some physicists have speculated about more exotic quantum phenomena that might allow genuine faster-than-light information transfer. Theoretical proposals include quantum tunneling across macroscopic distances, where particles could potentially appear on the far side of barriers without having traveled through the intervening space. Other ideas involve exploiting the quantum vacuum itself, the seething sea of virtual particles that fills apparently empty space, as a medium for faster-than-light communication. The quantum vacuum represents one of the most mysterious aspects of modern physics. Far from being truly empty, the vacuum is filled with fluctuations of energy and virtual particle pairs that constantly appear and disappear. These quantum fluctuations have measurable effects, influencing the behavior of atoms and the properties of light itself. Some researchers have wondered whether the quantum vacuum might serve as a kind of cosmic information network, allowing for instantaneous communication across arbitrary distances. Advanced civilizations might also discover ways to manipulate the fundamental constants of physics within localized regions of space-time. If the speed of light could be altered in specific areas, or if the relationship between space and time could be modified, entirely new possibilities for faster-than-light travel might emerge. Such modifications would require understanding physics far beyond our current knowledge, but they represent the kind of breakthrough that could revolutionize space travel and communication. Another intriguing possibility involves the manipulation of extra dimensions that may exist beyond the three spatial dimensions we experience directly. Many modern theories of physics, including string theory, propose that our universe has additional spatial dimensions that are normally hidden from us. If these extra dimensions exist, they might provide shortcuts that allow faster-than-light travel through higher dimensional space. Imagine 2 points on the surface of a cylinder that are far apart when measured along the curved surface, but very close when measured through the interior of the cylinder. Similarly, points that are distant in our three-dimensional space might be close neighbors when accessed through higher dimensional paths. Discovering how to move through these extra dimensions could provide the ultimate shortcut for cosmic travel. Some theories even suggest that the apparent speed of light limitation applies only within our particular three-dimensional slice of a higher dimensional reality. In the full higher dimensional space, different rules might apply, allowing for forms of motion and communication that transcend the limitations we observe in our reduced dimensional perspective. As we contemplate these various alternatives to conventional faster-than-light travel, we begin to see that the universe may be far more flexible and accommodating than our current understanding suggests. While the speed of light represents a fundamental limit within our ordinary experience of space and time, the deeper structures of reality might provide pathways that circumvent this limitation entirely. The search for alternatives to light speed restrictions reflects humanity's deepest aspirations to explore, communicate, and understand the cosmos without the constraints imposed by vast distances and long travel times. Whether through exotic particles, manipulated space-time geometry, quantum mechanical phenomena, or entirely unknown physics, the universe may yet reveal ways to transcend the apparent boundaries that currently confine us to our small corner of the cosmic ocean. What if there are other ways for information to travel faster than light, hidden mechanisms that the universe uses to connect distant regions in ways we have not yet discovered? The cosmos might hold secrets that make the impossible not just possible, but inevitable. In 1962, physicist Gerald Feinberg proposed one of the most audacious ideas in modern physics: the existence of particles that are forever condemned to travel faster than light. He called these hypothetical entities tachyons, from the Greek word tachys, meaning swift. Unlike every known particle in the universe, which must struggle against increasing energy requirements as they approach light speed, tachyons would inhabit a mirror realm of physics, where exceeding light speed is not just possible but mandatory. The mathematical foundations for tachyons emerge naturally from Einstein's equations when we consider what happens to particles with imaginary mass. This might sound like pure fantasy, but imaginary numbers are fundamental tools in physics, appearing in quantum mechanics, electromagnetic theory, and many other well-established areas of science. When Einstein's energy equation E=mc² is applied to particles with imaginary mass, the result is particles that must always travel faster than light. To understand how tachyons would behave, imagine a universe where all the normal rules of motion are inverted. Ordinary particles require energy to speed up and release energy when they slow down. Tachyons would do exactly the opposite. As a tachyon gains energy, it slows down, approaching but never quite reaching light speed. As it loses energy, it speeds up, potentially reaching infinite velocity when its energy drops to zero. This backwards relationship between energy and velocity creates a strange symmetry in the universe. Just as ordinary matter cannot be accelerated to light speed because doing so would require infinite energy, tachyons cannot be decelerated to light speed for the same reason. Light speed becomes an impermeable barrier, separating two distinct realms of existence: the subluminal world of ordinary matter and the superluminal realm of tachyons. The existence of tachyons would revolutionize our understanding of causality and the flow of time. From the perspective of some observers, tachyons would appear to travel backward through time, arriving at their destination before leaving their origin. This doesn't necessarily mean that tachyons actually travel into the past, but rather that the order of events involving tachyons would depend on the observer's reference frame. Consider a tachyon signal sent from Earth to a distant star. From Earth's perspective, the signal might travel normally from past to future, reaching the star after it was sent. But from the perspective of an observer moving at high speed relative to Earth, the same signal might appear to arrive at the star before it was transmitted from Earth. This reversal of temporal order doesn't violate causality as long as the signal cannot carry meaningful information that could be used to create paradoxes. The potential for tachyons to enable faster-than-light communication has captivated scientists and science fiction writers alike. A tachyon transmitter could theoretically send messages across galactic distances instantaneously, allowing real-time conversations between civilizations separated by thousands of light years. Space explorers could maintain contact with Earth regardless of how far their journeys carried them into the cosmos. But tachyon communication would come with bizarre complications due to the relativity of simultaneity. Messages sent using tachyons might arrive in different orders, depending on the motion of the sender and receiver. A conversation conducted through tachyon signals could become scrambled, with replies arriving before questions and effects preceding causes from certain perspectives. Some physicists have proposed that these temporal complications might be resolved if tachyons can only travel in specific directions through space-time, or if they interact with matter in ways that preserve causality despite their faster-than-light motion. Others suggest that the universe might have built-in mechanisms that prevent tachyons from carrying information that could create logical paradoxes. The search for experimental evidence of tachyons has proven frustratingly elusive. Scientists have looked for tachyon signatures in cosmic ray experiments, particle accelerator collisions, and astronomical observations. Some researchers have reported possible tachyonic phenomena, such as particles that appear to arrive at detectors before they could have traveled there at light speed. But these observations have never been conclusively verified. One of the challenges in detecting tachyons is that they might not interact with ordinary matter in easily observable ways. If tachyons have very weak interactions with normal particles, they could pass through our detectors without leaving detectable traces. Alternatively, tachyons might exist, but be produced only under extreme conditions that we cannot yet replicate in laboratory experiments. The mathematical properties of tachyons create additional complications for their detection. In quantum field theory, tachyonic fields can lead to vacuum instability, where the ground state of the universe becomes unstable and transitions to a lower energy configuration. This instability might prevent stable tachyons from existing, or it might indicate that our universe is not in its true ground state. Some theories suggest that tachyons might have existed in the early universe, but disappeared as the cosmos evolved. During the inflationary epoch, when space expanded exponentially in the first fraction of a second after the Big Bang, tachyonic fields might have driven this rapid expansion before decaying into ordinary matter and energy. In this scenario, tachyons would be relics of cosmic creation, rather than contemporary phenomena. The concept of tachyonic matter has also influenced speculative proposals for faster-than-light travel. If tachyons exist and can be controlled, they might serve as the basis for propulsion systems that exceed light speed. A spacecraft surrounded by a field of tachyonic matter might be able to travel through the superluminal realm, bypassing the normal restrictions that confine ordinary matter to subluminal velocities. However, such applications would face enormous theoretical and practical challenges. Containing and controlling tachyonic matter would require understanding physics far beyond our current knowledge. The energy requirements might be astronomical, and the potential for unintended consequences could be severe. A tachyonic drive that malfunctions might send its spacecraft backward through time or scatter it across multiple dimensions. The study of tachyons has also led to important insights about the structure of physical theories themselves. Tachyonic instabilities in quantum field theories often signal the presence of phase transitions or symmetry breaking, phenomena that play crucial roles in our understanding of particle physics and cosmology. Even if tachyons themselves don't exist as stable particles, tachyonic fields might be essential components of theories that describe how the universe evolved from its earliest moments. String theory, one of the most ambitious attempts to unify all the forces of nature, includes tachyonic modes that must be eliminated for the theory to be consistent. These tachyonic instabilities indicate that certain string configurations are unstable and will decay into more stable arrangements. The process of eliminating these instabilities, called tachyon condensation, has led to new insights about how fundamental particles and forces might emerge from more basic string dynamics. Some researchers have proposed that tachyons might exist in parallel universes or extra dimensions that are normally inaccessible to us. In these hidden realms, tachyonic matter could be as common as ordinary matter is in our universe. Occasionally, tachyons from these parallel domains might leak into our space-time, creating brief, difficult-to-detect signatures that could explain some unexplained phenomena in particle physics experiments. The philosophical implications of tachyon existence extend far beyond physics. If particles can travel faster than light and potentially influence past events, our understanding of free will, determinism, and the nature of time itself would need fundamental revision. The universe might be far more interconnected than we imagine, with events in distant regions instantly affecting conditions everywhere else through tachyonic interactions. Yet the absence of confirmed tachyon detections after decades of searching has led many physicists to conclude that tachyons probably don't exist as real particles. The universe seems to conspire against faster-than-light travel, implementing subtle but effective mechanisms that prevent violations of causality. This cosmic censorship might reflect deep principles of physics that we don't yet fully understand. Alternative theories suggest that what we interpret as the impossibility of tachyons might actually indicate limitations in our current theoretical frameworks. More advanced physics might reveal that tachyonic phenomena are possible, but require understanding aspects of reality that transcend our current three-dimensional, single-timeline perspective of the universe. The search for tachyons continues to inspire new experimental techniques and theoretical insights. As our technology becomes more sophisticated and our understanding of fundamental physics deepens, we might eventually discover whether these faster-than-light particles exist in our universe or remain forever confined to the realm of mathematical possibility. Even if tachyons prove to be impossible, their theoretical study has already enriched our understanding of space-time, causality, and the deep structures that govern physical reality. They represent the kind of bold, imaginative thinking that drives scientific progress, pushing us to question our assumptions and explore the furthest boundaries of what might be possible. Tachyons emerge from the quantum world as particles that defy the limits we know. They challenge our understanding of what is possible and impossible, suggesting that the universe might hold surprises that transcend our current comprehension. Could they hold the key to faster-than-light travel, or do they represent a cosmic impossibility that reveals deeper truths about the nature of reality itself? In the strange realm of quantum mechanics, where particles can exist in multiple states simultaneously and reality seems to emerge only when observed, there exists a phenomenon so bizarre that even Albert Einstein struggled to accept it. Quantum entanglement allows two particles to become mysteriously connected across any distance, sharing an instantaneous bond that transcends the normal limitations of space and time. When one entangled particle is measured, its partner immediately responds, regardless of whether they are separated by millimeters or millions of light years. Einstein famously dismissed this phenomenon as spooky action at a distance, believing it revealed flaws in quantum theory rather than genuine features of reality. He argued that no influence should be able to travel faster than light, and the apparent instantaneous connection between entangled particles seemed to violate this fundamental principle. Einstein preferred to believe that entangled particles carried hidden information that predetermined their behavior, eliminating the need for faster-than-light communication. For decades, this disagreement between Einstein and the founders of quantum mechanics remained a philosophical debate rather than an experimental question. The mathematics of quantum theory clearly predicted entanglement effects, but the technology to test these predictions with sufficient precision didn't exist. It wasn't until the 1970s that physicist John Bell developed a way to distinguish experimentally between Einstein's hidden variable theories and genuine quantum entanglement. Bell's theorem showed that if quantum entanglement is real, then measurements on entangled particles must violate certain mathematical inequalities that any theory based on local hidden variables must satisfy. Experiments testing Bell's inequalities have consistently supported quantum mechanics, confirming that entanglement represents a genuine feature of reality rather than an illusion created by incomplete knowledge. To understand how quantum entanglement works, imagine two particles created simultaneously in a process that conserves certain properties like spin. According to quantum mechanics, neither particle has a definite spin direction before measurement. Instead, each exists in a superposition of all possible spin states. But because the total spin must be conserved, the particles become entangled, forming a single quantum system where measuring one particle instantly determines the state of the other. This connection persists regardless of distance. If entangled particles are separated and carried to opposite sides of the galaxy, measuring the spin of one particle along any chosen axis instantly determines what the measurement result would be for its partner along the same axis. The correlation appears to be instantaneous, suggesting that information somehow travels between the particles faster than light. However, the strange nature of quantum mechanics prevents this correlation from being used for faster-than-light communication. While the measurement results are perfectly correlated, they appear random to any individual observer. The person measuring the first particle sees a seemingly random sequence of results, and the person measuring the second particle sees a similarly random sequence. Only when they compare their results through conventional, slower-than-light communication channels do they discover the mysterious correlations. This inability to transmit information through entanglement reflects a deeper principle in quantum mechanics. The randomness of individual measurement results is fundamental, not just a consequence of incomplete knowledge. Each measurement genuinely produces a random outcome, even though these random outcomes are perfectly correlated between entangled particles. Quantum entanglement has been demonstrated not just with simple two-particle systems, but with increasingly complex arrangements involving multiple particles, photons, atoms, and even small molecules. Scientists have created entangled networks where measurements on one particle affect multiple partners simultaneously, and they have maintained entanglement across increasingly large distances using satellites and fiber optic networks. Perhaps most remarkably, entanglement can be extended through time as well as space. Researchers have demonstrated temporal entanglement, where particles become correlated with other particles that don't even exist yet. A measurement performed on a particle today can be entangled with the results of measurements that will be performed on particles created in the future, suggesting that quantum correlations transcend our ordinary understanding of temporal sequence. The implications of quantum entanglement extend far beyond academic curiosity. Entanglement forms the foundation for emerging technologies like quantum computing, quantum cryptography, and quantum teleportation. Quantum computers exploit entanglement to perform certain calculations exponentially faster than classical computers, potentially revolutionizing fields from cryptography to drug discovery. Quantum teleportation, despite its name, doesn't involve moving matter faster than light. Instead, it uses entanglement to transfer the complete quantum state of one particle to another distant particle. The original particle is destroyed in the measurement process, while its quantum information reappears in the destination particle. This process requires classical communication to complete, ensuring that no information travels faster than light overall. However, some researchers have speculated about more exotic applications of entanglement that might enable genuine faster-than-light effects. If entanglement could be harnessed to create macroscopic correlations, it might become possible to influence distant objects instantaneously. Such applications would require extending quantum effects from the microscopic realm of individual particles to the macroscopic world of everyday objects. The challenge lies in the fragility of quantum entanglement. Entangled states are extremely sensitive to environmental interference, a phenomenon called decoherence. Any interaction with the surrounding environment tends to destroy entanglement, causing entangled particles to behave like independent classical objects. Maintaining entanglement in macroscopic systems would require unprecedented control over environmental conditions. Some theoretical proposals suggest that entanglement might be exploited through clever indirect methods that sidestep the apparent prohibition on faster-than-light information transfer. For example, if entangled particles could be used to influence the probability of certain events without directly transmitting information, it might be possible to create faster-than-light effects that don't violate causality. Other researchers have explored whether entanglement might be connected to the structure of space-time itself. Some theories propose that space-time emerges from underlying quantum entanglement networks, suggesting that the fabric of reality is woven from countless entangled connections between fundamental constituents. In this view, entanglement wouldn't just occur within space-time, but would actually create space-time. This perspective leads to intriguing possibilities for manipulating space and time through controlled entanglement. If space-time geometry can be influenced by changing entanglement patterns, it might be possible to create shortcuts through space, alter the flow of time, or even access parallel universes through quantum tunneling effects. The study of entanglement has also revealed deep connections between quantum mechanics and information theory. Entanglement can be quantified as a form of information that exists in the correlations between particles rather than in the particles themselves. This entanglement entropy provides a new way to understand black holes, cosmology, and the fundamental nature of information in the universe. Some physicists have proposed that consciousness itself might be based on quantum entanglement effects in the brain. While highly speculative, these theories suggest that entanglement could explain the unity of conscious experience and the apparent non-local nature of mental phenomena. If consciousness involves quantum entanglement, it might be possible to create direct mind-to-mind communication or even consciousness transfer through controlled entanglement manipulation. The exploration of entanglement has also led to discoveries about the foundations of reality itself. Quantum mechanics reveals that the classical notion of objects as independent entities with definite properties is fundamentally incorrect. Instead, reality consists of interconnected systems where the properties of individual components cannot be understood in isolation from their relationships with other components. This holistic view of reality suggests that the universe is far more interconnected than our everyday experience indicates. Every quantum interaction creates entanglements that link particles across vast distances and time spans. We exist within a cosmic web of quantum correlations that connects every atom in our bodies to particles throughout the observable universe. Recent experiments have pushed the boundaries of entanglement to ever larger scales and longer distances. Scientists have demonstrated entanglement between particles on Earth and satellites in orbit, between particles separated by hundreds of kilometers through fiber optic networks, and between increasingly massive objects approaching the boundary between quantum and classical behavior. These advances bring us closer to understanding whether entanglement effects might scale up to macroscopic levels, where they could enable practical faster-than-light applications. While current physics suggests that such scaling faces fundamental limitations, the history of quantum mechanics is filled with surprises that defied theoretical expectations. The phenomenon of quantum entanglement also raises profound questions about the nature of locality and realism. Bell's theorem shows that either the world is non-local, with distant events instantly affecting each other, or it's non-realistic, with particles lacking definite properties before measurement. Most physicists accept non-locality, concluding that entanglement represents genuine, faster-than-light correlations. But this non-locality doesn't violate relativity, because it cannot be used to send signals or information faster than light. The correlations exist, but they cannot be exploited for communication or control. This subtle distinction preserves causality while allowing for the mysterious connections that entanglement creates. As we contemplate the implications of quantum entanglement, we begin to see that the boundaries between separate objects, distant locations, and different moments in time are far more fluid than our classical intuition suggests. The universe operates according to principles that transcend our ordinary understanding of space, time, and causality. Entanglement reveals that information and influence can propagate through channels that bypass the normal restrictions of space-time, even if these channels cannot be used for conventional communication. The quantum realm challenges our concepts of what is possible and impossible, suggesting that reality operates according to rules that are far stranger and more wonderful than we typically imagine. Quantum mechanics challenges the very concept of speed and locality, showing us that information might travel in ways we cannot yet fully comprehend. While we cannot use entanglement to send messages faster than light, it demonstrates that the universe contains hidden connections that transcend the apparent limitations of distance and time. Could these quantum mysteries hold keys to understanding forms of faster-than-light phenomena that we have not yet discovered? Deep within the mathematical equations of Einstein's general relativity lies one of the most captivating possibilities in all of physics: the existence of tunnels through space-time that could connect distant regions of the universe through shortcuts that bypass the normal constraints of distance and travel time. These theoretical structures, known as wormholes, offer a tantalizing vision of cosmic highways that might make faster-than-light travel possible without violating the fundamental principles of relativity. The concept of wormholes emerged in 1916, just 1 year after Einstein published his general theory of relativity. Austrian physicist Ludwig Flamm discovered that the equations describing a black hole could be extended to describe a tunnel connecting two separate regions of space-time. This mathematical bridge, later called an Einstein-Rosen bridge, after Einstein and his colleague Nathan Rosen studied it further, represented the first theoretical wormhole. To visualize how a wormhole might work, imagine the universe as a vast sheet of paper representing the three-dimensional space we inhabit. Normally, traveling from one side of the paper to the other requires moving across the entire surface, a journey that could take millions of years, even at light speed for cosmic distances. But if the paper could be folded so that distant points touch each other, a small hole punched through both layers would create a shortcut that dramatically reduces the travel distance. In the real universe, this folding would occur in dimensions beyond our normal three-dimensional experience. A wormhole would bend space-time through higher dimensional space, creating a tunnel that connects distant regions through a path that is much shorter than the normal route through ordinary space. A traveler entering one mouth of the wormhole might emerge from the other mouth in a completely different galaxy, having crossed vast distances in mere moments. The mathematics of general relativity permits several different types of wormholes, each with unique properties and challenges. The simplest wormholes would be eternal, existing as permanent features of space-time that connect distant regions for unlimited time. More exotic varieties might be traversable in only one direction, allowing passage from one mouth to the other but not in reverse. Still, others might exist only briefly, opening and closing so quickly that nothing could pass through them. Perhaps the most intriguing type is the traversable wormhole, which would allow matter, energy, and information to pass safely from one mouth to the other. Such wormholes would need to remain stable long enough for spacecraft to enter one mouth, travel through the tunnel, and emerge from the other mouth. Creating and maintaining such stability presents enormous theoretical and practical challenges. The primary obstacle to stable wormholes is their tendency to collapse catastrophically. According to general relativity, any wormhole that forms naturally would pinch itself closed almost instantly, creating a barrier that prevents anything from passing through. The gravitational forces within the wormhole throat would compress space-time so severely that the tunnel would squeeze shut before even light could traverse it. Keeping a wormhole open would require a form of matter or energy with very unusual properties. Specifically, it would need negative energy density, something that pushes space-time apart rather than pulling it together, like ordinary matter. This exotic matter would need to be threaded through the wormhole throat, creating an outward pressure that counteracts the natural tendency toward gravitational collapse. Negative energy might sound like pure fantasy, but quantum mechanics suggests that such phenomena are possible under certain circumstances. The quantum vacuum, despite being empty of particles, fluctuates with virtual particle pairs that briefly appear and disappear. Under special conditions, these fluctuations can create regions of space with negative energy density, as demonstrated in phenomena like the Casimir effect. However, the amount of negative energy required to stabilize a macroscopic wormhole would be enormous, possibly exceeding the total positive energy in the observable universe. Even if such quantities of exotic matter could be assembled, controlling and containing it would require technology far beyond anything we can currently imagine. Recent theoretical work has explored whether quantum effects might provide alternative mechanisms for wormhole stabilization. Some researchers have proposed that quantum entanglement between the two mouths of a wormhole might create the necessary exotic properties without requiring classical negative energy matter. In this scenario, the wormhole would be stabilized by purely quantum mechanical effects rather than exotic matter. The relationship between wormholes and quantum entanglement has become an active area of research, with some physicists proposing that entangled particles might actually be connected through microscopic wormholes. This idea, known as the ER equals EPR conjecture, suggests that Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement are different descriptions of the same underlying phenomenon. If this connection between wormholes and entanglement proves correct, it might be possible to create macroscopic wormholes by scaling up quantum entanglement effects. Advanced civilizations might learn to entangle large objects or even regions of space-time, potentially creating navigable wormholes through controlled quantum engineering. The discovery of natural wormholes would revolutionize our understanding of cosmic geography. The universe might be riddled with shortcuts that make distant galaxies as accessible as neighboring planets. Ancient wormhole networks could connect regions that formed in the early universe, creating a cosmic transportation system that spans the entire observable cosmos. Some scientists have speculated that advanced extraterrestrial civilizations might have already discovered how to create artificial wormholes, using them to build galactic empires that span vast distances. Such civilizations could maintain instantaneous communication and transportation across their domains, making them effectively immortal from the perspective of less advanced species confined to single star systems. The time travel implications of wormholes add another layer of complexity and possibility. If the two mouths of a wormhole could be moved relative to each other at high speeds, time dilation effects would cause them to age at different rates. Eventually, the mouths might connect different moments in time, as well as different locations in space, creating a time machine as well as a transportation device. Such temporal wormholes would raise profound questions about causality and free will. Travelers might be able to visit their own past, potentially creating paradoxes where effects precede their causes. Some physicists argue that the universe has built-in protection mechanisms that prevent such paradoxes, perhaps by destroying wormholes before they can be used for time travel. The search for evidence of natural wormholes has focused on astronomical observations that might reveal their gravitational effects. A wormhole mouth would appear as a massive object that bends light from background sources, creating gravitational lensing effects similar to those produced by black holes. However, distinguishing between wormhole signatures and those of other exotic objects remains extremely challenging. Some researchers have proposed that the mouths of wormholes might be visible as unusual astronomical objects, with properties that cannot be explained by conventional astrophysics. These might appear as sources of matter and energy that seem to violate conservation laws from our perspective, because material entering one mouth would disappear from our local region and emerge elsewhere in the universe. The study of wormholes has also led to insights about the fundamental nature of space-time itself. Some theories propose that space-time at the smallest scales might be filled with a foam of tiny wormholes that constantly appear and disappear. This quantum foam could provide the foundation for larger-scale structures and might offer clues about how macroscopic wormholes could be constructed. String theory, which attempts to unify all the forces of nature, naturally includes wormhole-like solutions that connect different regions of the higher dimensional spaces in which strings vibrate. These theoretical wormholes might provide pathways between parallel universes or different phases of cosmic evolution, offering possibilities that transcend even the most optimistic science fiction scenarios. The practical challenges of wormhole construction and navigation would be staggering even if the theoretical obstacles could be overcome. Spacecraft entering a wormhole would experience extreme tidal forces that could tear apart any material object. The geometry of the wormhole throat might be so exotic that normal matter cannot survive the journey, requiring entirely new forms of technology and protection. Navigation through wormhole networks would require understanding the topology of higher dimensional space and developing methods for predicting where different wormhole paths lead. A cosmic GPS system would be needed to prevent travelers from becoming lost in the maze of shortcuts that might crisscross the universe. Despite these challenges, the study of wormholes continues to inspire new ideas about the nature of space-time and the possibilities for faster-than-light travel. Even if traversable wormholes prove to be impossible, their theoretical investigation has already led to important insights about quantum gravity, black hole physics, and the fundamental structure of reality. The equations of general relativity that describe wormholes are the same equations that successfully predict the behavior of GPS satellites, the merger of neutron stars, and the shadows of black holes. This gives us confidence that wormholes, even if they don't exist in nature, represent genuine features of the mathematical landscape that describes our universe. As our understanding of quantum gravity and higher dimensional physics advances, we may discover new ways to create the exotic conditions necessary for wormhole formation. Future breakthroughs in physics might reveal that the apparent impossibility of faster-than-light travel through wormholes is merely a limitation of our current perspective rather than a fundamental law of nature. The concept of wormholes also raises profound questions about the ultimate nature of distance and separation in the universe. If space-time can be folded and tunneled through shortcuts that make distant regions adjacent, then our ordinary notions of near and far, here and there, might be fundamentally misleading. The cosmos might be far more connected and accessible than our surface-level observations suggest. Wormholes provide a fascinating possibility for transcending the apparent limitations of light-speed travel by bending space-time itself to create cosmic shortcuts. While the challenges are enormous, they represent the kind of bold thinking that drives scientific progress and expands our understanding of what might be possible in a universe far stranger than we typically imagine. Wormholes offer the tantalizing prospect of bending space-time itself to make faster-than-light travel a reality. But can they be more than just theoretical ideas, or do they represent a cosmic possibility waiting to be discovered and harnessed by sufficiently advanced civilizations? The dream of traveling at the speed of light has captivated human imagination since we first understood what light speed represents. To move at 299,792,458 meters per second would transform us into beings of pure energy, crossing vast cosmic distances in what would feel like moments from our perspective. Yet this dream faces obstacles so fundamental that they seem to represent absolute barriers written into the very fabric of reality itself. The most immediate challenge to light-speed travel lies in the energy requirements predicted by Einstein's relativity. As any object with mass approaches light speed, the energy needed to accelerate it further increases dramatically. At 90% of light speed, an object requires more than twice as much energy to accelerate as it would need starting from rest. At 99% of light speed, the energy requirement increases by a factor of 7. At 99.9%, it jumps to more than 22 times the rest energy. This escalating energy demand follows a precise mathematical curve that approaches infinity as velocity approaches light speed. To accelerate even a single proton to exactly light speed would require infinite energy, which is clearly impossible. The universe simply doesn't contain enough energy to propel any massive object to the cosmic speed limit, no matter how advanced our technology becomes. But perhaps the energy barrier isn't as absolute as it first appears. Consider that our current rockets achieve velocities of only a few kilometers per second by burning chemical fuels, while light travels at nearly 300 million meters per second. The gap between our current capabilities and light speed is so enormous that even modest improvements in propulsion technology could yield dramatic results. Nuclear propulsion systems could potentially achieve velocities measured in thousands of kilometers per second, bringing us closer to a significant fraction of light speed. Fusion rockets, if we could master controlled nuclear fusion, might reach even higher velocities by converting matter directly into energy with much greater efficiency than chemical reactions. More exotic propulsion concepts envision using antimatter as fuel, annihilating it with normal matter to produce pure energy, according to Einstein's famous equation E equals mc squared. Antimatter reactions release 100% of the mass as energy, compared to less than 1% for nuclear fusion, and a tiny fraction of 1% for chemical combustion. An antimatter rocket could theoretically achieve velocities approaching a significant fraction of light speed, perhaps 10 to 20%. While still far from light speed itself, such velocities would make interstellar travel feasible within human timescales. A journey to the nearest star system, Alpha Centauri, might take 20 to 40 years instead of tens of thousands of years. However, antimatter presents its own formidable challenges. Producing antimatter requires enormous amounts of energy, and storing it safely seems nearly impossible with current technology. Antimatter annihilates instantly upon contact with any normal matter, making containment systems extremely complex and potentially dangerous. The total amount of antimatter ever produced by humanity could barely power a light bulb for a few minutes. Some visionary proposals look beyond conventional reaction mass entirely, imagining propulsion systems that push against the fundamental structure of space-time itself. These concepts recognize that space is not truly empty, but filled with quantum fields and virtual particles that might serve as a medium for exotic propulsion mechanisms. The Alcubierre warp drive represents perhaps the most famous of these space-time manipulation concepts. Rather than accelerating through space, the Alcubierre drive would contract space in front of a spacecraft while expanding space behind it, creating a wave of distorted space-time that carries the ship along. The spacecraft itself would remain stationary within its local bubble of normal space-time, never exceeding light speed locally, while the bubble itself moves through the cosmos at arbitrary velocities. From the perspective of someone aboard an Alcubierre drive spacecraft, the journey would feel completely normal. They would experience no acceleration forces, no time dilation effects, and no increase in mass. Meanwhile, outside observers would see the spacecraft effectively traveling faster than light, crossing vast distances in impossibly short times. The mathematics of general relativity permits Alcubierre drive solutions, suggesting that such propulsion is not forbidden by the fundamental laws of physics. However, the practical requirements are staggering. Creating the necessary space-time distortions would require exotic matter with negative energy density, potentially exceeding the mass energy of the entire observable universe. Recent theoretical refinements have reduced these energy requirements somewhat, but they remain far beyond anything achievable with foreseeable technology. Some proposals suggest that the energy could be reduced to more manageable levels, perhaps equivalent to the mass of a large planet, by optimizing the geometry of the warp bubble and using more efficient space-time manipulation techniques. Even if the energy requirements could be solved, the Alcubierre drive faces other fundamental challenges. Quantum effects within the warp bubble might destabilize the space-time distortion, causing the drive to fail catastrophically. The spacecraft might be unable to control its trajectory or communicate with the outside universe while the drive is active. Most problematically, turning off the drive might be impossible once it's activated, trapping travelers in a runaway warp bubble. Alternative space-time manipulation concepts explore different approaches to achieving faster than light-effective velocities. Some proposals involve creating closed time-like curves that loop through space-time, allowing spacecraft to arrive at their destinations before they departed. Others suggest manipulating extra dimensions that might exist beyond our normal three-dimensional experience. The concept of space-time engineering recognizes that sufficiently advanced civilizations might develop techniques for manipulating the fundamental structure of reality itself. Just as we have learned to engineer materials at the atomic scale, future civilizations might engineer space-time at the Planck scale, creating exotic geometries that enable faster than light travel. Such engineering would require understanding physics far beyond our current knowledge. We would need to comprehend quantum gravity, the unification of all fundamental forces, and possibly the existence of parallel universes or extra dimensions. The technological requirements might be so advanced that they represent genuine magic from our current perspective. Yet the history of human technological development suggests that today's impossibilities often become tomorrow's everyday realities. Powered flight seemed impossible until the Wright brothers achieved it in 1903. Space travel was pure fantasy until Sputnik launched in 1957. Instantaneous global communication was unimaginable until the internet connected the world. Perhaps faster than light travel will follow a similar trajectory, remaining impossible until some breakthrough insight reveals the key to transcending light speed limitations. The breakthrough might come from unexpected directions, quantum computing, artificial intelligence, nanotechnology, or discoveries in fundamental physics that we cannot currently anticipate. The psychological and biological challenges of light-speed travel might prove as difficult as the technical obstacles. Even if we could achieve such velocities, the human body and mind might not be capable of surviving the experience. The forces involved in acceleration and deceleration could exceed human tolerance, requiring new forms of protection or perhaps fundamental modifications to human physiology. Time dilation effects would create profound challenges for light-speed travelers. While a journey to a distant star might take only months from the traveler's perspective, decades or centuries could pass on Earth. Astronauts would return to find that everyone they knew had aged and died, that human civilization had evolved beyond recognition, that the very reasons for their journey had become obsolete. These temporal displacements might make light-speed travel psychologically impossible, even if it becomes technically feasible. The social and emotional costs of becoming unstuck in time could outweigh any benefits from rapid interstellar travel. Future space travelers might choose slower journeys that keep them synchronized with their home civilization. Robotic spacecraft might prove more suitable for light-speed travel than human crews. Artificial intelligences could potentially survive the enormous forces and temporal displacements involved in relativistic travel. Robot explorers traveling at light speed could survey vast regions of the galaxy, transmitting their discoveries back to Earth through conventional electromagnetic signals. Such robotic exploration missions could revolutionize our understanding of the cosmos, while avoiding the biological and psychological challenges that would affect human travelers. We might discover that light-speed travel becomes routine for artificial beings, even if it remains forever impossible for biological life. The development of advanced artificial intelligence might itself provide alternative solutions to the challenges of cosmic exploration. Rather than physically traveling to distant stars, we might send detailed information about human consciousness and civilization, allowing artificial intelligences to reconstruct human-like beings at remote destinations. In effect, we could achieve faster-than-light exploration by transmitting ourselves as information rather than matter. These speculative scenarios illustrate how the apparent impossibility of light-speed travel might be circumvented through approaches that transcend our current understanding of travel, identity, and consciousness. The universe might offer pathways to cosmic exploration that don't require moving matter at light speed, but achieve equivalent results through information transfer or consciousness manipulation. As we contemplate the challenges and possibilities of light-speed travel, we begin to see that the question might not be whether such travel is possible, but whether it represents the most effective approach to cosmic exploration. The universe might offer alternative pathways that achieve the same goals through radically different methods. The dream of light-speed travel continues to inspire new approaches to propulsion, space-time manipulation, and cosmic exploration. Even if classical light-speed travel proves forever impossible, the pursuit of this dream drives innovations that expand our understanding of physics and our capabilities for exploring the cosmos. While achieving light-speed travel seems impossible with our current understanding, the dream of faster-than-light exploration still burns brightly in the minds of scientists and dreamers alike. Perhaps the breakthrough will come not from conventional acceleration, but from entirely new approaches that transcend our current limitations through deeper understanding of space-time's hidden properties. As we stand at the threshold of a new era in physics, where quantum computers process information in ways that seemed impossible just decades ago, where gravitational waves ripple through space-time exactly as Einstein predicted, and where the deepest mysteries of dark matter and dark energy challenge our understanding of reality itself, we must ask whether our current perception of light speed as an absolute barrier might itself be a limitation waiting to be transcended. The history of physics is filled with revolutionary discoveries that transformed apparent impossibilities into everyday realities. Isaac Newton's gravity seemed to act instantaneously across infinite distances until Einstein revealed the finite speed of gravitational influences. Classical physics suggested that energy could only be absorbed and emitted continuously until Max Planck discovered quantum mechanics and the discrete nature of energy packets. The atom was considered indivisible until scientists learned to split nuclei and release the enormous energies hidden within. Each breakthrough came from recognizing that our current theories, however successful, represent approximations of deeper truths rather than final answers. Einstein's relativity superseded Newton's mechanics not by proving Newton wrong, but by revealing the limited domain where Newtonian physics applies accurately. Similarly, quantum mechanics didn't eliminate classical physics, but showed its boundaries and limitations. Today's prohibition against faster-than-light travel might suffer a similar fate as our understanding of fundamental physics advances. The speed of light appears absolute within the framework of current theories, but future discoveries might reveal new frameworks, where light speed represents just one characteristic velocity among many, rather than an insurmountable barrier. One promising avenue for such discoveries lies in quantum gravity, the long-sought theory that would unify Einstein's general relativity with quantum mechanics. Current physics treats spacetime as a smooth continuum, described by Einstein's equations, while quantum mechanics describes matter and energy in terms of discrete packets and probability waves. These two pillars of modern physics remain fundamentally incompatible, suggesting that both represent incomplete descriptions of deeper reality. Several candidate theories of quantum gravity propose that space and time themselves might be quantized at the smallest scales, existing as discrete units rather than continuous fields. In this view, space-time would be composed of fundamental building blocks, perhaps as small as the Planck length of approximately 10 to the minus 35 meters, far smaller than any particle we have ever observed. If space-time has this discrete structure, then the apparent smoothness we observe at larger scales would be an emergent property, like the way a digital photograph appears continuous when viewed from sufficient distance despite being composed of individual pixels. The properties we associate with space-time, including the speed of light, might be determined by the characteristics of these fundamental space-time units. String theory, one of the most ambitious attempts to describe quantum gravity, proposes that all particles and forces arise from vibrating strings in higher dimensional space. In string theory, our familiar three-dimensional space might be just a slice through a higher dimensional reality where different physical laws apply. The speed of light might represent a limitation only within our particular dimensional slice, while the full higher dimensional space permits faster-than-light phenomena. Some string theory solutions describe branes, which are higher dimensional surfaces that could contain entire universes. If our universe exists on one such brane, while other branes exist nearby in higher dimensional space, it might be possible to access these parallel realms where different speed limits apply. Advanced civilizations might learn to navigate between branes, effectively teleporting across vast distances without traveling through normal space. Loop quantum gravity, an alternative approach to quantum gravity, suggests that space-time might have a network-like structure at the smallest scales, resembling a cosmic mesh or foam rather than a smooth continuum. In this framework, particles and energy might be able to tunnel through the quantum foam, taking shortcuts that bypass the normal restrictions of light-speed travel. These quantum gravity theories remain highly speculative, but they illustrate how future physics might reveal pathways around the apparent light-speed barrier. The key insight is that space-time itself might not be fundamental, but rather an emergent phenomenon arising from deeper structures that operate according to different rules. The study of dark matter and dark energy has already revealed that our understanding of the universe remains profoundly incomplete. These mysterious components comprise approximately 95% of the universe's content, yet their nature remains entirely unknown. Dark matter interacts gravitationally, but appears invisible to electromagnetic radiation. Dark energy drives the accelerating expansion of the universe through mechanisms we cannot explain. The existence of such vast unknown realms of physics suggests that major discoveries await us. Dark matter might interact through forces we have not yet discovered, potentially enabling new forms of propulsion or communication that transcend light speed limitations. Dark energy, which can accelerate cosmic expansion faster than light, might be harnessed to create localized regions of space-time expansion that enable faster-than-light travel. Some physicists speculate that dark matter might exist in a shadow sector of physics, parallel to our familiar electromagnetic and nuclear forces, but interacting with ordinary matter only through gravity. This shadow sector might have its own photons, its own chemistry, and its own speed limits that differ from those in our visible sector. Learning to access the shadow sector might provide pathways to faster-than-light phenomena. The concept of extra dimensions, central to many modern physics theories, offers another avenue for transcending light-speed barriers. If our universe has more than the 4 dimensions of space-time that we experience directly, then our 3-dimensional perspective might severely limit our understanding of what is possible. Consider how a 2-dimensional being living on the surface of a sphere would perceive travel between distant points. From their perspective, the shortest path would follow the curved surface of the sphere, requiring significant travel time, even at light speed. But a 3-dimensional being could take a shortcut straight through the sphere's interior, dramatically reducing the travel distance. Similarly, if our universe has extra spatial dimensions, then what appears to be vast distance in our 3-dimensional space might correspond to much shorter distances when measured through higher dimensional space. Particles or information might be able to take shortcuts through these extra dimensions, effectively traveling faster than light from our limited 3-dimensional perspective. The development of quantum field theory in curved space-time has revealed that the quantum vacuum itself might contain enormous untapped energies and exotic properties. The vacuum is not truly empty, but seethes with virtual particle pairs that constantly appear and disappear. Under extreme conditions, these quantum fluctuations might be harnessed to create the exotic matter needed for wormhole stabilization or warp drive operation. Recent proposals in theoretical physics suggest that the quantum vacuum might be manipulated through carefully designed electromagnetic fields or gravitational configurations. If successful, such manipulation might create regions of negative energy density without requiring exotic matter from outside sources. This could provide the key to practical faster-than-light travel through space-time engineering. The emergence of quantum information science has revealed deep connections between information, entanglement, and the structure of space-time itself. Some theorists propose that space-time might literally be constructed from quantum entanglement networks, with the geometry of space emerging from patterns of quantum correlations rather than existing as a fundamental backdrop. If this entanglement-based view of space-time proves correct, then manipulating quantum entanglement might allow direct manipulation of space-time geometry. Advanced quantum technologies might create entanglement networks that effectively shrink distances between remote locations or create tunnels through space-time that enable faster-than-light travel. The field of quantum computing has already demonstrated phenomena that seemed impossible from classical perspectives. Quantum computers can factor large numbers exponentially faster than classical computers and can simulate quantum systems that would require classical computers larger than the observable universe. These achievements suggest that quantum mechanics contains resources we are only beginning to understand. Future developments in quantum technology might reveal ways to exploit quantum mechanics for space-time manipulation or faster-than-light communication. Quantum teleportation already achieves instantaneous state transfer between distant particles, and while current quantum teleportation cannot transmit information faster than light, future discoveries might find ways around this limitation. The study of black holes has revealed that these extreme gravitational objects possess properties that challenge our understanding of information, time, and causality. Recent theoretical work suggests that black holes might be connected to other regions of space-time through microscopic wormholes, and that information falling into black holes might be preserved through quantum mechanical processes we don't yet understand. These discoveries about black hole physics might provide clues about how to manipulate space-time more generally. If black holes can preserve information through exotic quantum processes, then similar processes might enable faster-than-light information transfer or travel under controlled conditions. The development of artificial intelligence and machine learning has begun to reveal patterns in complex data that human scientists cannot detect directly. Future AI systems might discover relationships in the laws of physics that point toward new phenomena enabling faster-than-light travel. AI could simulate conditions that are impossible to create experimentally, potentially revealing exotic states of matter or space-time that permit superluminal phenomena. As we look toward the future of physics, we must remain open to the possibility that our current understanding represents just the beginning of a much larger story. The universe has consistently proven to be stranger, more complex, and more wonderful than our theories predict. The prohibition against faster-than-light travel might be another limitation waiting to be transcended through deeper understanding. The coming decades will likely bring revolutionary discoveries in fundamental physics as we probe deeper into the quantum realm, explore higher dimensional spaces, and develop technologies that can manipulate matter and energy in ways that seem magical today. These advances might reveal that the speed of light, rather than being an absolute barrier, is simply one characteristic of our local region, of a much larger and more flexible reality. The search for faster-than-light phenomena reflects humanity's deepest aspirations to explore, understand, and transcend the apparent limitations of our cosmic environment. Whether through quantum gravity, extra dimensions, space-time engineering, or entirely unexpected discoveries, the future may hold keys to unlocking the ultimate mysteries of speed, distance, and time. The future is full of possibilities that we can barely imagine today. Perhaps one day we will discover that the speed of light was just the beginning of our journey through the stars, the first step toward understanding a universe where distance becomes irrelevant and time itself becomes a tool for exploration rather than a barrier to overcome. If humanity ever succeeds in breaking through the light-speed barrier, we would cross more than just a cosmic boundary. We would enter a realm where our most fundamental assumptions about reality, causality, and the nature of existence itself would require complete reconsideration. The implications of faster-than-light travel extend far beyond mere transportation, touching the deepest questions about consciousness, free will, the nature of time, and our place in the vast cosmic story. Consider what it means to live in a universe where cause and effect follow predictable sequences, where earlier events lead to later consequences, where the past is fixed and the future remains open to possibility. Our entire understanding of rational thought, moral responsibility, and meaningful action depends on this temporal ordering. We make decisions based on past experience, expecting those decisions to influence future outcomes in comprehensible ways. Faster-than-light travel could shatter this fundamental framework. If information or influence can travel faster than light, then effects might precede their causes from certain perspectives. A message sent faster than light could potentially arrive before it was transmitted, creating logical paradoxes that challenge the very notion of causality. We might witness consequences before understanding what caused them, or even influence events that had already occurred. This breakdown of normal causality would force us to reconsider the nature of free will and moral responsibility. If effects can precede causes, then our actions might influence events that have already happened from our perspective. We might become responsible for shaping a past that we thought was immutable, or discover that our future decisions have already constrained our present choices in ways we cannot comprehend. The philosophical implications become even more profound when we consider the nature of consciousness and personal identity. Our sense of self depends partly on the continuity of our memories and experiences through time. We understand ourselves as beings who learn from the past and plan for the future, maintaining coherent identities despite constant physical and mental changes. In a universe where faster-than-light phenomena allow effects to precede causes, the nature of consciousness itself might require redefinition. We might discover that consciousness operates according to principles that transcend normal temporal sequence, that our awareness somehow spans multiple moments simultaneously, or that individual identity represents just one perspective on a more complex, multidimensional existence. The possibility of faster-than-light travel also raises questions about the ultimate nature of distance and separation. We currently understand ourselves as discrete beings occupying specific locations in space and time, separated from other beings by measurable distances that require finite time to cross. This spatial separation seems to guarantee a form of privacy and individuality that we consider essential to personal identity. If space-time shortcuts or instantaneous communication become possible, then the boundaries between separate individuals might become less meaningful. We might discover that consciousness can extend across vast distances instantaneously, that minds can merge and separate in ways that challenge our notions of individual identity, or that the apparent separation between beings represents an illusion created by our limited perspective on higher dimensional reality. These possibilities would revolutionize our understanding of relationships, love, empathy, and human connection. Instead of being isolated islands of consciousness occasionally communicating across the void, we might discover that we are more like waves on an ocean of awareness, temporarily individuated expressions of a deeper, unified consciousness that transcends spatial and temporal boundaries. The implications for knowledge and understanding would be equally profound. Our current scientific method depends on the principle that information travels at finite speeds, allowing us to establish clear relationships between causes and effects. We design experiments based on the assumption that influences propagate predictably through space and time, enabling us to isolate variables and understand their relationships. In a universe where faster-than-light phenomena are possible, the nature of scientific investigation might require fundamental revision. We might need entirely new methods for understanding relationships between events when normal temporal sequence cannot be assumed. The concept of objective observation might become meaningless if the act of observation can influence past events, or if multiple incompatible timelines coexist simultaneously. Yet such challenges might also open pathways to forms of knowledge that are currently unimaginable. If consciousness can access information faster than light, we might develop intuitive ways of understanding that transcend rational analysis. We might discover that the universe contains layers of meaning and significance that are invisible from our current temporally limited perspective. The social and political implications of faster-than-light capabilities would be staggering. Human civilization has developed within the constraints imposed by light-speed communication, creating structures of governance, economics, and social organization based on the assumption that coordination across large distances requires significant time delays. Instantaneous communication across galactic distances would make possible forms of civilization that span multiple star systems while maintaining real-time coordination. We might develop galactic governments, interstellar economies, and cultural networks that treat vast cosmic distances as easily traversable. The concept of Earth as an isolated world would become obsolete as humanity spreads across the galaxy while maintaining intimate connections. But such expansion might also create new forms of inequality and conflict. Civilizations with faster-than-light capabilities would possess overwhelming advantages over those confined to slower-than-light existence. The gap between superluminal and subluminal societies might become so vast that meaningful communication or cooperation becomes impossible, creating a form of cosmic apartheid based on technological capability. The existential implications touch our deepest questions about meaning and purpose. Much of human philosophy and religion has developed around the premise that we live in a universe where we are fundamentally alone, separated by vast distances from other possible forms of consciousness, struggling to find meaning and purpose within the brief span of individual lifetimes. Discovery of faster-than-light phenomena might reveal that this apparent isolation represents an illusion. We might learn that consciousness pervades the universe in ways we have never suspected, that intelligence and awareness operate on cosmic scales through mechanisms that transcend our current understanding, or that individual human lives represent temporary expressions of vast cosmic processes. Such revelations could provide profound comfort by suggesting that we are not alone in the universe, that our struggles and achievements matter on cosmic scales, and that death might not represent the absolute termination we currently fear. But they might also diminish the apparent significance of individual human experience by revealing it to be just one minor variation in an infinite symphony of consciousness. The relationship between faster-than-light travel and time travel creates additional layers of philosophical complexity. If faster-than-light phenomena allow influence to propagate into the past, then the entire structure of history might become fluid and changeable. Past events that we consider fixed and immutable might be subject to modification by future actions. This possibility would transform our understanding of tradition, heritage, and cultural continuity. The civilizations, achievements, and tragedies that we consider to be permanent parts of human history might be alterable through sufficiently advanced technology. We might bear responsibility not just for shaping the future, but for constantly recreating the past in ways that align with our evolving understanding and values. The implications for meaning and purpose become paradoxical in such a fluid, temporal environment. If past and future become equally malleable, then the significance of present choices might either increase dramatically as we become responsible for shaping all of history, or decrease to nothing, as any consequences can always be undone through later temporal manipulation. Religious and spiritual traditions would face unprecedented challenges in adapting to faster-than-light realities. Most spiritual systems assume some form of linear progression, whether through individual lifetimes, historical development, or cosmic evolution. The breakdown of normal temporal sequence would require fundamental revision of concepts like karma, divine justice, salvation, and spiritual growth. Yet faster-than-light phenomena might also provide validation for mystical traditions that have always claimed consciousness can transcend normal spatial and temporal limitations. Meditation practices that aim to achieve unity with universal consciousness, prayer traditions that assume instantaneous connection with divine awareness, and mystical experiences of timelessness might be revealed as accurate perceptions of deeper reality rather than subjective illusions. The aesthetic and artistic implications would be equally transformative. Human art has always been shaped by our experience of time, sequence, and causality. Music unfolds through temporal progression, stories develop through cause and effect relationships, and visual arts capture moments within the flow of time. Art forms that incorporate faster-than-light phenomena might develop entirely new aesthetic principles based on non-linear causality, simultaneous multiple perspectives, or the direct transmission of experience across vast distances. We might create artistic expressions that can only be fully appreciated by consciousness operating outside normal temporal constraints. As we contemplate these profound implications, we begin to see that the question of faster-than-light travel is really a question about the ultimate nature of reality itself. Are we isolated beings struggling against cosmic loneliness, or are we interconnected expressions of universal consciousness? Is time a fundamental river that carries us toward an uncertain future, or is it a dimension that conscious beings can navigate as freely as we currently move through space? The search for faster-than-light phenomena reflects humanity's deepest yearning to transcend the apparent limitations that confine us to our small corner of space and time. Whether or not such phenomena prove possible, the very act of seriously contemplating them expands our understanding of what existence might mean in a universe far stranger and more wonderful than our everyday experience suggests. Perhaps the ultimate significance of faster-than-light possibilities lies not in their practical applications but in their power to remind us that reality extends far beyond the boundaries of our current perception. They invite us to imagine forms of existence that transcend our current limitations, while remaining grounded in rigorous scientific thinking. Could faster-than-light travel bring us closer to the ultimate truth of the universe? The answers we seek may lie not in crossing a physical boundary, but in discovering that consciousness itself operates according to principles that transcend the apparent limitations of space and time, revealing deeper dimensions of reality that have always been present but hidden from our ordinary awareness. As our journey through the mysteries of light speed and the possibilities that might transcend it draws to a close, we find ourselves not with definitive answers, but with something far more valuable, an expanded sense of wonder about the nature of reality and our place within it. We have explored realms where the impossible might become inevitable, where the boundaries that seem absolute might prove to be merely temporary limitations awaiting the next breakthrough in human understanding. Throughout this exploration, we have discovered that the speed of light represents far more than just a cosmic speed limit. It serves as a gateway to understanding the deepest principles that govern space, time, matter, and energy. In questioning whether anything can exceed this fundamental constant, we have been led to examine the very foundations of existence itself. We have seen how Einstein's revolutionary insights revealed that space and time are not separate, absolute entities, but aspects of a unified fabric that can be stretched, compressed, and curved. We have explored how approaching light speed transforms the experience of time itself, making cosmic journeys possible within human lifetimes, while the rest of the universe ages around the traveler. These relativistic effects remind us that reality operates according to principles that transcend our everyday intuitions. Our investigation of alternatives to conventional light-speed travel has revealed a universe rich with exotic possibilities. Theoretical particles called tachyons might inhabit a mirror realm where faster-than-light motion is mandatory rather than forbidden. Quantum entanglement demonstrates that information and influence can be correlated instantaneously across any distance, suggesting that the universe contains hidden connections that transcend normal spatial limitations. Wormholes offer the tantalizing possibility of shortcuts through space-time itself, potentially allowing travelers to cross vast cosmic distances by tunneling through higher dimensional space. While the practical challenges are enormous, requiring exotic matter and energy sources that we cannot currently imagine, the mathematical foundations of these ideas rest on the same equations that successfully describe black holes, gravitational waves, and the expansion of the universe. The Alcubierre warp drive and similar space-time engineering concepts suggest that sufficiently advanced civilizations might learn to manipulate the fabric of reality itself, creating waves of distorted space-time that carry spacecraft at effective speeds, far exceeding light. Such technologies would represent the ultimate expression of our species' drive to explore and understand the cosmos. Yet perhaps the most profound insights from our journey come not from specific proposed mechanisms for faster-than-light travel, but from recognizing how much we still do not understand about the universe we inhabit. Dark matter and dark energy comprise 95% of cosmic content, yet their nature remains completely mysterious. The unification of quantum mechanics and general relativity continues to elude us, suggesting that revolutionary discoveries await in the realm of quantum gravity. Extra dimensions, string theory, and the quantum nature of space-time itself point toward a reality far more complex and strange than our three-dimensional, single-timeline experience suggests. The universe might contain hidden layers of existence where different physical laws apply, where distance becomes irrelevant, and where consciousness itself operates according to principles we have not yet discovered. These possibilities remind us that the history of science has been a story of repeatedly discovering that the universe is far stranger and more wonderful than we initially imagined. Each generation of scientists has confronted apparent limitations that seemed absolute, only to discover that these limitations reflected the boundaries of current understanding rather than fundamental barriers written into the nature of reality. The transformation from viewing Earth as the center of the universe to understanding our solar system as one among billions, orbiting within a single galaxy among countless others, exemplifies how scientific progress expands our Bélian-Savart perspective. Similarly, our current perception of light speed as an absolute barrier might represent just another limited viewpoint, awaiting transcendence through deeper understanding. The implications of faster-than-light phenomena extend far beyond transportation and communication. They touch the deepest questions about consciousness, free will, the nature of time, and the ultimate meaning of existence. If cause and effect can become scrambled, if consciousness can extend across vast distances instantaneously, if the past becomes as malleable as the future, then our entire understanding of what it means to be conscious beings in a physical universe would require fundamental revision. These philosophical dimensions remind us that the search for faster-than-light travel is really a search for understanding our place in the cosmic order. Are we isolated beings struggling against overwhelming distances and brief lifespans? Or are we expressions of a universe that contains hidden mechanisms for transcending apparent limitations? The answer might determine not just our technological future, but our spiritual and existential development as a species. As we look toward the future, we can envision scenarios that seem like pure fantasy, yet remain grounded in rigorous scientific thinking. Artificial intelligences might discover patterns in physics that reveal pathways to faster-than-light phenomena. Quantum computers might simulate conditions that suggest new approaches to space-time manipulation. Advances in fundamental physics might reveal that consciousness itself operates through mechanisms that transcend normal spatial and temporal constraints. Whether or not faster-than-light travel becomes possible, the pursuit of this goal drives innovations that expand human capability and understanding. The technologies developed for advanced space propulsion could revolutionize energy production, materials science, and our ability to explore the solar system. The theoretical insights gained from studying exotic space-time geometries deepen our understanding of black holes, the Big Bang, and the ultimate fate of the universe. Perhaps most importantly, contemplating faster-than-light possibilities encourages us to maintain a sense of wonder and humility about the nature of reality. In a universe where quantum particles can exist in multiple states simultaneously, where empty space seethes with virtual particle pairs, where black holes can evaporate through Hawking radiation, and where the expansion of space itself can exceed light speed, we should remain open to discoveries that challenge our current assumptions. The cosmos has consistently revealed itself to be more interconnected, more dynamic, and more responsive to consciousness than our initial theories predicted. From quantum entanglement to the observer effect in quantum mechanics, from the role of information in black hole physics to the possibility that space-time itself emerges from deeper quantum processes, we find hints that mind and matter, consciousness and cosmos, might be more intimately connected than we currently understand. These connections suggest that the ultimate breakthrough in faster-than-light travel might come not from engineering exotic matter or manipulating space-time geometry, but from discovering new relationships between consciousness and physical reality. If awareness itself operates according to principles that transcend normal spatial and temporal limitations, then learning to work with these principles might provide the key to cosmic exploration. As you drift towards sleep, carrying these ideas into the realm of dreams where normal limitations often dissolve, remember that every great advance in human understanding began with someone willing to imagine possibilities that seemed impossible. The Wright brothers envisioned powered flight when heavier-than-air machines were considered fundamentally impossible. Einstein imagined curved space-time when geometry was thought to be absolutely fixed. Quantum pioneers explored probabilities and superpositions when reality was assumed to be deterministic and classical. The next breakthrough in our understanding of cosmic speed limits might come from directions we cannot currently anticipate. It might emerge from artificial intelligence research, from advances in consciousness studies, from discoveries about the nature of dark matter and dark energy, or from entirely unexpected observations that force us to reconsider our basic assumptions about reality. Whatever form these discoveries take, they will likely reveal that the universe is even more remarkable than our current theories suggest. The speed of light, rather than representing an absolute barrier, might prove to be just one characteristic of our local region in a far larger and more flexible reality. The cosmos might contain pathways to exploration and understanding that make our current limitations seem as quaint as the belief that humans could never fly. The journey toward understanding whether anything can exceed the speed of light continues, driven by humanity's deepest aspirations to explore, to understand, and to transcend apparent boundaries. Whether through exotic physics, consciousness research, or entirely unknown approaches, the universe may yet reveal that the speed of light was indeed just the beginning of our journey through the infinite possibilities that await us among the stars. In embracing these possibilities, we embrace the fundamental mystery and wonder of existence itself, remaining open to discoveries that could transform not just our technology, but our understanding of what it means to be conscious beings in an endlessly surprising and magnificent universe.